Stand-Up Physicist. I'm working on a rank 1 field theory to unify gravity and electromagnetism. This particular problem has been around since the 1760s and remains the oldest unsolved riddle in theoretical physics. So given that long time period, you might say, well, hasn't a rank 1 field theory been tried before? Absolutely it has been. But it has been tried at the wrong time, either too early or not anymore, or it has been asked in the wrong context. And I hope to show in today's broadcast that it's going to be really hard to sell no matter what, due to how training goes today. There is no good record of failures. The reason is kind of simple. Let's say you do a calculation and it's not working. Well, you take that calculation and you throw it away. Failures have no offspring. It's very hard to find a paper that discusses a rank 1 field theory. I have found 3, and they only talk about it in 2 paragraphs, which means they hardly go into it at all before dismissing it. So I'm going to have to speculate a bit as to why that's the situation. We tried to unify gravity and EM probably a little bit too early by looking very closely at the theory for light. And here it is. This is called the EM Lagrangian. Now, a Lagrangian is everything that can happen inside of a box that involves electricity and magnetism. If you do certain calculations with this, you can actually derive the Maxwell field equations which govern how electrons and photons interact. I've done that calculation. It takes about an hour and 15 minutes and fills up 6 blackboards. Looks really interesting. But this Lagrange density has a problem, at least from a modern perspective. If you decide to take this particular derivative, you will find that it equals 0. And because it equals 0, this Lagrange density cannot be quantized. And therefore, while it's good for classical work, it's not fundamental. We'll go ahead anyway and notice a problem that would have been obvious to the folks who came up with this in the 1800s. And that is, there's a subtraction in there. And what is subtraction? Well, you've got a bunch of stuff, and then you subtract, and you have less stuff. In this case, we start out with 16 little parts to the second rank tensor, and we subtract away 10, leaving us with 6. So that brings up the obvious question. What are those other 10 guys doing? Well, they must be doing something really important, because these 6 do some really important stuff. The entire electronics industry is based on this. So if we go ahead and say we're not going to do that subtraction, no. Subtraction, bad. Now we've got a new Lagrange density. And I've actually seen this in the literature. But that's where it's in the wrong context. See, now that we've got these extra 10 involved, we must be able to do more physics. But that paper was about EM and EM only, which seems kind of silly. Why add in all this extra stuff if you're not going to do something new? And it's also technically wrong, because this thing here, this normal derivative acting on a 4 potential, does not transform like a tensor. And therefore, it's not the stuff of physics. You must use a covariant derivative. Must substitute that d for a triangle. It's just the way that the world goes. Alright? We'll not worry about it. Let's take this other one over here, substitute it in. And this isn't just a D for a triangle. This is a pretty significant change. Because what happens is that you bring in the derivative of a metric via the connection. And when you start to have work with the connection, that how a metric changes, that's when you start sounding like you're working on gravity. So let's just hope that we're working on EM and gravity. And so now we're going to try and do the gem Lagrangian. Cool. Now, I had never worked with Lagrangians before, and two people gave me technical criticism of it. But they also really put me down for being very wrong about those two technical details. And I'm actually quite proud that I was able to separate the kind of personal attack from the technical and use their technical objections. So when I first decided to add in a new current because we had all this new work to do, I said, why don't I make it just like EM? And the only difference really being that I've decided to use this little M here, but otherwise it's the same. Well, this good professor, he said, you see that minus sign in front of that first J? And the minus signs over here? Because of those two minus signs, like charges will repel. And that is the way that EM works. But it is not the way gravity works, so this Lagrange density is stupid. Well, it was right. And in two of those three papers that I was found in the literature, they said the same thing. They said if you really copy EM closely, you will find that mass charges should repel from each other, and they don't, so it's wrong, so it's silly. Go on, move. Well, this problem has a simple solution. Instead of subtracting that current, why don't we just add it? Now, if you do that, then that has a sign that is the opposite of this, and that means that two like charges will attract each other. And that is how gravity behaves. So, now we have the situation where a like electric charge repels, but a like mass charge attracts, which is exactly how gravity and light work. Great. But then I decided in a news group to discuss the trace of this particular matrix, which is just kind of the stuff down the diagonal, and I wrote it like this because I thought, well, you know, I kind of seen people discuss this. And somebody said, no, 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 that's absolutely foolish. This is absolutely illegal because you must have one of those indices up and the other indice down. And I said, well, simple to do. I just have to rewrite almost everything I ever wrote and make sure one's up and one's down. And you might say, well, that sounds kind of trivial. But this thing actually does a huge job that will also kind of make it hard to sell. The job that it does is that this is a scalar field, which means it really is just one number. And it does not mess up the EM Lagrange part of the gem Lagrangian. It's perfectly fine with this thing being non-zero. Well, how do things get mass? Right now, you have this the Lagrangian for EM, and you use something called the Higgs particle and the Higgs mechanism to introduce mass. And they are spending several $billion, quite literally, in Europe to detect the Higgs particle. And what I'm saying is that the Higgs mechanism is not necessary. There will be a scalar field. It's just the trace of the unified field metric, and that will be it. So you should be able to detect these particles, but it's not due to the Higgs mechanism at all. It's just the trace of the field strength tensor. A simple approach, but fundamentally different from the Higgs particle and all the papers that have been written on it. In 1915, Albert Einstein and Hilbert proposed a new theory for gravity that came to be known as General Relativity. And by 1919, it had passed 3 very difficult tests. And so from that point on, people believed that all theories of gravity have to be at least a rank 2 or more, and that they must be nonlinear. It's very reasonable to imagine why it has to be rank 2. We have plenty of experimental data that indicates that gravity depends on a metric that can change. So if you have a scalar Lagrangian and you vary it with this rank 2 tensor, then you end up with a rank 2 field equation. The logic is that simple. The logic is that solid. But what I do is I look into the Lagrangian and I see a symmetry. I see a symmetry between changes in the potential and changes in the metric. That arises because I went from a standard derivative to a covariant derivative. And that's how I can link a theory that is all about potential, which would be the classical EM Lagrangian, and a theory that's all about metric, the Hilbert action, and find a link between the two. General Relativity's field equations are nonlinear, and people actually consider this to be a criteria for any proposal. It must be nonlinear. Well, that nonlinearity causes severe problems for people who want to quantize it. It's just not going along with the program. Why do they have such conviction? Well, because of certain thought experiments. I'm going to discuss one done by Price in a review article on general relativity that I rather liked at the time. Imagine a box. It's got 6 particles. Imagine another box. 6 particles. Now these 2 boxes are going to be attracted to each other because of gravity. Now imagine that I took one of those 5 particles and turned it into motion. Would this particle be able to tell whether the particles were in motion, 5 particles in motion, or I had the 6 that were lying still? And I think it's reasonable to say this box wouldn't be able to tell the difference. And because this box couldn't tell the difference between 5 particles moving really rapidly and 6 particles just hanging out, it actually makes the theory nonlinear. Now that was fine when I was just doing gravity, but now I'm doing gravity and electromagnetism at all times. And these 6 particles are all neutral. What happens to the thought experiment if I make them charged? Now I have my 6 particles as before, and 6 particles over here, but they are all electrically charged. And what I want to do, according to the thought experiment, is to take out one of these electrons and, oh, this is a problem. Because these guys are going to now move around a lot, but they're going to have 5 units of electric charge, not 6. Well, we have experimental as well as theoretical data that says you cannot, no matter what you do, destroy an electron like that. Because you cannot destroy an electron like that, we cannot do Price's thought experiment if we make the particles charged. And you will find this happens to all these thought experiments that people do to try and show that gravity must be nonlinear. If you make the particles charged, then you can't do the experiment that the person wants to do, at least in their brain. Because you have to violate electric charge conservation, and we have great data to say that you simply cannot do that. So because the thought experiment cannot be done in theory, it means that you cannot take its conclusion. We cannot take the conclusion of Price's thought experiment that the theory must be nonlinear. That does not mean the theory has to be linear, but it means the thought experiment that you used to use to believe that it had to be nonlinear is no longer there. Now, it takes a huge amount of effort to really understand general relativity. To get a sense of it, look no further than this book, Misner, Thorne, and Wheeler, Gravitation. We're talking 1,280 pages of rather technical stuff. But what's amazing is this quote from one of the authors. How can physics live up to its true greatness except by a new revolution in outlook which dwarfs all past revolutions? And when it comes, will we not say to one another, "Oh, how beautiful and simple it is! How could we ever have missed it for so long?" John Archibald Wheeler. Well, I think my proposal is simple. It fit on a placard just that big. But it's going to be a very difficult sell because it takes a lot of work to understand the rank 2 theory that's nonlinear. And my theory is rank 1. And it is linear. So let's turn to the literature for guidance. Let's look to Goldilocks and the 3 bears. Alright, so what's the story? Well, you got these bears, and they're kind of suburban bears. They're in a house, they're chowing on porridge. But they want to stay in touch with nature, so they take a walk. And there's this little girl, gets a little lost, sees a house, says, "I think I'll just enter." I can't believe this chick. But she goes in, and she sees some food. So she becomes the food critic, tries all 3. This one too hot, that one too cold, this one just right. And so she chows down the whole darn thing. I would have left at this point, but she decides it's time to lounge. So she tries one chair. Oh, that's too hard. That one's too soft. This one's perfect. Except she breaks the darn thing. Now at this time, I would be running. No, she decides, so much stress, I think I'll go sleep in the house. Tries one bed, tries another, ends up, finds the perfect bed, and she's out. So the suburban bears come back from the little stroll, and they're hungry. They're bears, for goodness sake. And they start eating their porridge, and Papa says, "Hey, someone's been eating my porridge." And Mama says, "Hey, someone's been eating my porridge." And Baby Bear says, "Hey, my porridge all gone." Now, bears maul people for food. You know, in the wild, they do that. I would expect these bears to be kind of angry, but they're suburban bears, so they decide to lounge. And Papa Bear says, "Hey, I'll just check out my chair." And says, "Hold it, someone's been sitting in my chair." Mama Bear's like, "Yeah, same here." And Baby Bear's like, "Someone has trashed my chair. Destroyed it." So Mama Bear says, "Well, perhaps this person's still in the house." Nobody but an insane person would be still in the house. They go upstairs. There is Goldilocks. Crashed, you know. Now, they're just hanging out around this bed. Now, these are bears. Okay? I mean, I think they are perfectly within their rights to maul Goldilocks. You know, put her dress outside, say no girl should come in here. Because if you do breaking and entering, eating people's food, destroying property, and violating the sanctity of people's bedrooms, well, good things are not going to happen. That'd be a good story, but it's a different story. Instead, what happens, Goldilocks wakes up, screams her head off, and runs out the door. Now, how does that relate to this story? Well, I am not a theoretical physicist. I'm not even a physicist. I was trained in biology. And the thing is that physicists think they are the smartest scientists of all. I mean, it's like so obvious to them. And they can like prove it because like in biology, they only got molecular biology because a bunch of physicists decided to do biology. So the whole concept that biologists could make a significant contribution to physics, I mean, that's you can't calculate that. That's too ridiculous. And this theory is very, very destructive. It's destructive because that 1,280-page book is really based on a rank 2 field theory that is nonlinear. And I'm saying, well, it actually should be a rank 1 field theory that is linear because you look into the Lagrangian for the symmetry that gives you a dynamic metric and connects a potential with a metric theory instead of just varying the action with a potential, which is what general relativity does. So if you no longer use a rank 2 field theory, then anything that's based off of that, well, kind of goes out the window. That would include, say, string theory. That would include, say, any work on black holes to date, where they really rely on that being nonlinear and therefore causing them all kinds of problems. All that work will have to be redone. That's sometimes the way change is in science. But I would actually say this is not a revolution. Because revolution is where you change the names of everything, but you don't really change what's going on. I say this is more evolution. Because if you remember that placard, what I did was I started with what we know best. EM theory really works good. And then I did a couple of tweaks here and there so that I could embrace gravity. And that's the way evolution is. It's mostly about being like your parents. And yet you've got to be a little bit different. And if those differences really are productive, then that's the way to go. And it doesn't matter who you step on or what happens. You have to go that direction. And I really feel that way. And that's why, in a certain sense, I'm here kind of sleeping and occasionally trying to, polish it up and make it look a little bit better. But I really think that there's a deep truth in this work. And I can understand why it has been found by physicists before. So thank you very much.
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass. And all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Math prof, rock star. Oh yeah. Math prof, rock star. He was young, he never thought that he would be a math prof, rock star. And after hours outside of his office, there's a line waiting full of girls who want to ask about their quadratic equations. She leans over the desk and twirls a pencil in her hair, complains the grade he gave her was way unfair. And all the professors, they laugh about it and they wish him well. The guys in the class are all just jealous as hell. Math prof, rock star.
What sources of information should one read and study up on if you want to answer that perennial question, what does it all mean? Well, there are the answers that our commercial culture gives. And there are so many things you can buy. And yet somehow it seems shallow. Then they're the answers that physics can give you. But those answers are in books like this, which, well, they're somewhat difficult to read. Maybe there's something in between the commercial and the truly physical. This is one source I have found. I have found that I really enjoy doing a close study of these sorts of products. Oh, my goodness.